So let's go ahead and just do an example. That's the best way to make sense of this. All right, so let me go back to my black ink here. Actually, you know what? Let me go ahead and go to blue. So example 2. Example 2. Now, we will let our curve t be t e of t and t squared, and we'll let our function x, y, z, so we're definitely talking about a curve in 3 space and a function of 3 variables, equals x, y squared, z, x, y squared, and z. Okay, so first of all, let's talk about what's going on here. We're going to form the composite function. We're going to be forming f of c of t. That's what we're going to be doing. Well, f of c of t, x, y, z, in this case, x is this thing, t. Y is this thing, e of t. It's the second. And z is this, t squared. Let's want to write everything out. Okay, now the gradient of f, that's it. We're just gonna build this step by step by step. That's all we're doing here. So the gradient of f is equal to, well, it's the first component is the first partial, the second component is the second partial, the third component is the third partial, right? And if you like the other notation, it's going to be df dx, it's going to be df dy, and it's going to be df dz. Okay, so now let's go ahead and actually compute that. The first partial, the derivative of this function with respect to x is y squared z. Y squared z. The derivative with respect to y is going to be 2xyz, 2xyz. And the derivative with respect to z is going to be xy squared. So this is my gradient of f. Okay. Now, my gradient of f evaluated at c of t. So now we'll take the next step. Now we'll do the grad of f evaluated at c of t, which is the actual expression that's in the definition for the chain rule. Well, all that says is I take my gradient f, this thing, and I just put in the values c of t in here. Well, x is t, y is e of t, z is t squared. So when I put these things into here, here's what I get. Y squared is just, so it's going to end up being t squared e of 2t, right? Y squared is just e of 2t. Z is t squared, so that's t squared e of 2t. 2 times x, which is t, y, which is e of t, z, which is t squared. I end up with 2t cubed e of t. And xy squared is t times e of t times t squared. I get t times e of, wait, y squared, e of 2t. Yes, there we go. E of 2t. Okay, so that takes care of this one. That's the grad of f evaluated at c of t. Now I just have to find c prime. Well, that's really, really simple. C prime of t. Well, here's my c right here. I'll just take the derivative of each one. That's it. The derivative of t is 1. The derivative of e of t is e of t. E to the t, sorry, not e of t, e to the t. And the derivative of t squared is 2t. Well, now I just form my dot product. So the gradient of f evaluated at c of t dotted with c prime of t, okay, it equals this vector dotted with this vector. Well, the dot product is this times that, so it's t squared. The dot product is not a vector. This times that, so it's t squared e to the 2t plus this times that, 2t cubed e to the 2t plus this times that, plus 2t squared e to the 2t. And that's it. Let's see if there's anything that I can combine here. T squared e to the 2t, 2t squared e to the 2t. Yes, there is. So it's going to be 3t squared e to the 2t plus 2 times t cubed e to the 2t. And that's my final answer. That's it. So let me go back. I was given some, a curve, and I was given a function, and I just hammered it out. I took the gradient as a function, as a vector in x, y, z. I evaluated it at c of t. In other words, I put these values in for x, y, z, and I got this. Okay, now it's the gradient vector expressed in t. I took the derivative of c, which is c prime. That's easy enough to do. Then I just took the dot product of those vectors. That's it. That's all that's going on here. So this happens to be the derivative of f of c of t. That's what this is equal to. This is equal to f of c of t prime. No, we want to definitely f prime c of t. That's it. That's all that's going on here. It's just a way of differentiating a composite function. Okay. Now, you're probably asking to yourself, okay, well, if I start with a function of t goes from r to r3, and then I take the function r3 to r, so it's a function of r to r. What I actually have is a function of t, right? Yes, it is just a function of t that you're differentiating. You're saying, well, wait a minute. If I found f of t up here, couldn't I just do this directly? Do I have to use the chain rule? And the answer is no, you don't have to use the chain rule. You can do it directly. Which one is better? Well, actually it just depends on the situation. It depends on the function. It depends on what you're doing. So that's all it is. So let's go ahead and actually do it directly just to confirm that you can do it directly. And I think it'll shed a little bit more light on this relationship between the curve and the function. So let's do this in blue again. So we said that f of x, y, z is equal to x, y squared z. And we said that c of t, let's just rewrite them over again. Let's see, what did we say c of t was? T e to the t and t squared. So now let's just form f of c of t. So f of c of t is equal to, well, x, y squared z. X is t, so that's t. Y squared is going to be e to the 2t, and z is going to be t squared. I'm just plugging those in, and I end up with t cubed e to the 2t. Well, now if I just take, this is just a function of t, so now if I just take df with respect to t, I end up getting, so it's going to be this times the derivative of that, which is going to be 2t cubed e to the 2t, plus that times the derivative of that, 3t squared e to the 2t. What do you know? You end up with the same exact answer. Which is better? Again, it just depends on your particular situation. Sometimes you want to sort of do it directly if it makes more sense. Sometimes you want to go ahead and use the chain rule if it makes more sense. The problem at hand will actually decide which one is better. Okay, so that is the chain rule. Thank you very much for joining us here at Educator.com, and we will see you next time. Take care. Bye-bye.